Hello dear students, let's see this very beautiful question of IIT-JEE 2008. This question involves perfectly inelastic and also perfectly elastic collision with a fixed incline. There is a common myth among students that in perfectly inelastic collision the body gets stuck to each other. This question breaks that myth. The bodies get stuck to each other if the collision is head-on, but in case of an oblique perfectly elastic collision the bodies do not get stuck. So let's try to go immediately into the question. The question states, a small block of mass capital M moves on a frictionless surface of an inclined plane as shown in figure. The angle of the inclined plane suddenly changes from 60 degree to 30 degree at point B. The block is initially at rest at A. Assume that the collision between the block and the incline are totally inelastic, and then some question are asked. So let me also draw my own figure and then proceed to solve the three parts of this comprehension. So here is the figure given in the question. First do the geometrical part, then we'll proceed to what is asked. This length is √3, so this is also √3, so this height will be this angle given is 60 degree, so this height will be √3 1060, that will become 3 meter. So this height is 3 meter, and this is 3 √3, this is 30, so this height will be 3 √3 1030, that is 3 meters. So this is 3, so this is also 3. So the heights we have calculated. Now the first part states the speed of the block at point B immediately after it strikes the inclined plane, second inclined plane. So let me calculate the speed just before hitting the inclined plane. So right now I am just erasing the other inclined plane, and for the sake of clarity I am going to draw this block by its simpler dot. So the block reaches here, and just before colliding with the other incline its velocity is say v, and because it has come up to here by traveling along the incline, so this velocity direction is along the first incline. And the forces are weight, normal, only the two forces, no friction, so its energy is conserved. So this velocity we can directly write by the gain in kinetic energy is equal to loss in potential G. So this velocity will be square root of 2gh, where h is the distance fallen, which is 3 meter. So that would be 2 into 10 into 3 square root, so that is our root 60 meter per second, and let it be like that. And now I am drawing the second inclined plane here. Let me send it in the backward direction, the extension of this thing, and let me draw the LOI, the line of impact to the second inclined plane. So the line of impact of the collision is normal to this inclined plane, so this is the line of impact like this. This is LOI, and obviously this is a normal to this inclined plane. So this angle is, this is 30 degree, this angle is 30 degrees, so this angle is also 30 degree, and this whole is 60 degree, so this remaining is also 30 degree. And if this angle is 30 degree, so is this angle is also 30 degree. Still we are before the collision, so I am going to make the component of this velocity along and normal to the inclined plane before the collision. So this is the component of velocity normal to the incline, normal to the LOI, and this is the component of velocity along LOI before collision. Component of velocity normal to LOI is v cos 30, and v is √60, cos 30 is √3 by 2, and let me take everything inside the root, so √60 into √3, and inside the square root 4. So how much that will be? That will be √45 meter per second. So this velocity is √45 meter per second, that is normal to LOI just before collision, and this component would be V sin 30. V sin 30 is root 60. V is the root 60, sin 30 is 1 by 2. So also take 1 by 2 inside the square root. So that will be root 15 meter per second. So this component is my root 15 meter per second. Now the collision is perfectly inelastic collision. In the perfectly inelastic collision, the coefficient of restitution E is 0. And what is the coefficient of restitution? Coefficient of restitution is the velocity of separation along LOI divide by velocity of approach of, and that is also along LOI. So if E is 0, that only means that the velocity of separation along LOI is 0. And this is the fixed incline, and it will remain fixed even after collision. So the relative velocity along LOI, there will not be any relative velocity along LOI. So after collision, it will not have any velocity along LOI. So this whole velocity, which was root 15 meter per second along LOI, that will vanish. So you can say that it will slide along the second inclined plane without bouncing. So after inclined plane, this whole velocity root 15 meter per second would be lost, but this velocity will be intact. So just after collision, the velocity of the block would be root 45 meter per second along inclined plane. And that is what is asked in the first question. The speed of the block at point B immediately after it strike the second inclined plane. So that answer is root 45 meter per second, and that is option B. And then again it is a smooth inclined plane. So then in the next question is asked, what is the velocity of the block at point C immediately before it leaves the second incline? So for this thing, I mean when this block reaches here, so what is its velocity? So that velocity, for that velocity we can again apply the energy conservation. So now suppose when it reaches this velocity becomes, say, Vc just before leaving this. So Vc square will be this velocity square root 45 whole square plus 2gh. H is the 3 meter, so that is a 45 plus 2 into 10 into 3, so that will be 105 this Vc square. So Vc will be square root of 105 meter per second, and which is our option B again. And then it is asked that in the third part, that had the collision been perfectly elastic at this moment, so what is the velocity of the block, the vertical component of the velocity of the block immediately after the second inclined plane? So again, the component of velocity normal to inclined plane do not change if the surface is smooth, but the only change is on the component along the LOI. So in the last case, when the perfectly elastic collision was that E was 0, so all the component along inclined plane was lost. But now when the collision is elastic, so this E is equal to 1. So velocity of separation along LOI will become velocity of approach along LOI. So what will happen? The velocity of approach along LOI was root 15 meter per second, and it is at rest. So just after collision, if the collision is perfectly elastic, so the component along LOI would be just reversed, because it is a perfectly elastic collision on a fixed inclined plane. So this component would be root 15 meter per second. And so the resultant velocity will be the vector sum of this root 45 and root 15, and that we can find the overall resultant component along vertical direction. So for that, let me remove this part. So this is the line of the second inclined plane. This angle is 30 degree. and this direction is the normal to inclined plane, mean the LOI. So it had one component along this direction. This component was root 45 meter per second. Its font size is a bit slow, so, and along LOI the component is root 15 meter per second. So this is the vertical line and this is horizontal line. This angle is 30 degrees, so this angle is 30 degree and this angle is 30 degree. So this root 15 will have a component along vertical direction, root 15 cos 30, and there will be some component along this direction, we don't have to bother. The root 45 will have some component here and some component here, and this component will be root 45 sin 30. So sin 30 is 1 by 2, cos 30 is root 3 by 2. So the net velocity along vertical direction will be root 15 cos 30 minus root 45 sin 30. So that is root 15 into root 3 by 2 minus root 45 by 2. So this is root 45 by 2 minus root 45 by 2. So answer is 0. So we will have option C. So what it means that just after collision from the second inclined plane, if the collision is perfectly elastic, the body will move horizontally because now it has a no vertical component. That's option C. Thank you.